let's continue. B part A, miscellaneous tips on applied math in physics. Now lecture 7, difference between Cartesian and tensor product. You see, Cartesian we already derived, explained in lecture 6. So this will move to in this case, to the tensor product. Now, the tensor, called also outer product, builds a higher order tensors from vectors. Tensor of order 1. You see, vectors are tensor of order 1, scalar are tensor of order 0. That's important. Now give an example, just to clarify. Let A is a vector and B is also a vector. But in this case, AI, EI, BJ, EJ. So, in the same vectors, I could write using AI, EI, upper index, or BJ, EJ, upper index, because vectors A and B are invariant. That's important word for you to remember, as I emphasized in previous lectures. So this outer product, or tensor product, is AIBJ, AIEJ. You see? This is equal, I call this combination here TIJ. TIJ, EI. Now, this case is an outer or tensor product EJ. That's the symbol. So it's the same AIBI, mu, E nu. You see this is a tensor product. The symbol is this TIJ. In this case, I can write I or J, doesn't matter, because I can use here, this is, I call this mu and nu, that's mu and nu. Likewise, these I can call, in this case, mu and nu. This is be mu, this will be nu. You see, because they are dummy indices, so there is no problem in writing this. Now, this important definition, EIJ acts on EJ. This leads to delta, the chronic delta IJ by definition. You see, likewise, EI, EJ is a metric GIJ, EI, EJ is a metric GIJ. You see, upper index, we used to say a contravariant. Lower is covariant. So this is a covariant matrix, and this is contravariant matrix. You see, you look at the indices you see, then you see if it's upper, is contravariant. If it's lower, is covariant. That's by convention. Now, since tensor is a map, consider the vector space capital V and its dual, capital V, in this case asterisk. You see, I just drew here, just for you to see clearly. This is a vector space, and this is its dual. See? This is an element, a vector V that belongs to capital V, and alpha is in this case is a vector, that's a dual vector that belongs to the dual space. So alpha, I just expand here, alpha nu E nu is a covector, because it belongs to the dual. And this is a vector in this case because it belongs to the vector space, by convention. Now I can use Greek letters, in general, in relativity theory we use Greek letters, not Roman as in classical mechanics, for instance. So note that the covector alpha acts on vector v leading to a scalar a. You see this figure here, alpha acts on the vector v leading to a real vector, a real scalar, real number. So by definition, as I wrote over here, you see nu e mu is delta nu mu, and by convention, you see the covector comes in the first slot. You see, that's it. This is a two slot, the first and the second one. By convention, okay, the covector comes in the first slot. So nu belongs to the dual space, and mu belongs to the vector space. So now, also by convention, lower indices are denoted as covariant and upper indices as contravariant, as I said previously. So it's important to remark, that's a very, very, very important, that the basis vectors a nu and a mu are abstract. That's very important, because this here we always use in intrinsic geometry. Okay, the basis vector, they are abstract. What do you mean by that? They are not unitary, neither orthogonal. Forget that. You see, the definition, okay, is by definition you can demonstrate. Okay, just you have to accept. Okay, that's why you have the delta chronic over here. Okay, since this contravariant and covariant, they are abstract, no unitary, neither orthogonal. That's very important for you, because in intrinsic geometry we don't talk about a unit vectors. Okay, so according to the figure over here, there's a particular case. You see, these I have two vectors. This example, I'm using only one vector and one covector. You see this here, alpha and nu, I just use, attention now, the covector comes in the first slot by convention, and this comes on the second slot. This is so these are scalar, real numbers, I can put outside this slot. So by definition, this over here is chronic delta. Chronic delta, the properties of chronic delta, in this case, I just eliminate mu and set nu. Or I could have a mu, v mu over there, because this here, nu is a dummy, so this is a real number. So that's one example, just to show you that in this case a map, okay, acts and leads to a scalar, which is the definition of a tensor. Tensor, don't forget that, is a map. Okay, in this case here is abstract. So when you deal with mechanical engineering, you have the curvilinear coordinates, okay, and we define the delta, the chronic delta, okay, using, in this case, vector position, okay, which is related to extrinsic geometry. Okay? In this case here is intrinsic geometry. That's why, again, chronic delta are abstract. Okay, that's it.